Hello everyone, welcome to OHM Institute. I am Surendra Reddy, faculty for electrical machines at OHM Institute, Hyderabad. So in today's video, I am going to discuss about the recent ISRO 2025 scientist paper, question paper analysis. Okay, and we will also discuss about the solutions for all electrical machines questions. Okay, so this exam was conducted recently, very recently, 2-3 days before. Okay, and most of the students knows what is the pattern of the ISRO question paper. Okay, so this question paper will have total of 95 questions. Okay, it is not 100 questions, total 95 questions, but the weightage will be 100 marks. Okay, total 95 questions, so 100 marks weightage. So what happens is, from technical subjects, 80 questions will be given and each question will carry 1 mark, and from aptitude 15 questions will be given but it will carry 20 marks. Okay, 15 questions, 20 marks, so the weightage of each question is more than 1 mark. All right, so now we will try to understand what is the weightage of this question paper, okay, in 2025. So from electrical machines subject, we have a highest number of questions, 27 questions came. Okay, and then from power system subject we have 26 questions. From power electronics subject we have 11 questions. So only these three subjects covers the entire technical question paper, I must say, because remaining subjects have very few number of questions. Okay, and the electrical circuits and control systems, both subjects has 5 questions each. Measurements subject carried 3 questions, and we got 2 questions from communications subject and 1 question from mathematics. Okay, that is a general question, but I can say you will read that question usually in power electronics and power systems also, but I must say mostly it is mathematics related. Okay, so and then we have 15 questions from aptitude subject. Aptitude question subject has overall 15 questions. Okay, so total 95 questions. Okay, 100 marks. Now what I am trying to do is, see, first of all, what is the need to discuss about this ISRO question paper is, there are upcoming exams, right? We have a gate exam in the month of February, and we have AEE exam which is around the corners in Andhra Pradesh state, and we mostly get AE exam also in Telangana state. Okay, so as there are number of exams around the corner and there are many public sector exams also going to happen, okay, very soon. Okay, public sector companies are recruiting engineers through their own exams. Okay, some of the companies, so that's why it is better to understand the questions that were given in the recent exams. Okay, so better to understand them, what level of questions they are asking, which subjects are carrying more weightage, and what topics they are covering mostly, is a numerical type paper or a theoretical type paper. All these things will help us to answer the next upcoming exams more easily. Okay, all right. Now what I am trying to do is that I will try to discuss about the electrical machines question. Okay, so electrical machine subject carried 27 questions. We will discuss one by one. Okay, all right. Now yes, here we have the question paper. Okay, this is ISRO 2025 question paper, and I just noted down electrical machines questions. Yes, the first question is from machines subject only, so I hope you are able to read this question. Okay, I just zoomed in the question paper. This is the actual question paper. Okay, so scientist question paper, electrical engineering. So in this first question we will try to solve, which is from electrical machines subject. Okay, all right. Now this is from transformer subject. Okay, just to read the problem. The secondary current IS in the below figure is how much? See, there was a transformer given which is having a turns ratio of 1:100. Primary side there is an inductive reactance. Secondary side there is a capacitive reactance along with resistance. Okay, but they are asking what is the current passing through secondary side of the transformer. 4 options are there. All right. See, we can answer this question in 2 ways. One is you transfer all the primary side parameters to secondary side. That is the first procedure. Or you transfer all secondary side parameters to primary side. So you make it like a single circuit, then we can easily answer how much current will flow through the transformer. As the question is specifically about answering secondary side current, you better transfer primary side parameters to secondary side. Okay, see what I'm trying to do. So just okay. So see, primary we have a reactance. What if I transfer this reactance to secondary side? You know, XL will become XL dash. Okay, and primary also has a supply voltage source. If I transfer this voltage to the secondary side, you see the turns ratio is 1 is to 100. Therefore this 100 volt, once it goes to the secondary side, it will become 10 into 100 by 1. That is the turns ratio, right? Okay, so it will be stepped up according to turns ratio. If a primary is 1, secondary is 100. If a primary is 10, secondary will become 1000. So the secondary side source voltage will become 1000 volt. Okay, and you just transfer this reactance also to the secondary side. So what will be XL dash? I hope those who studied transformers course, you know how to transfer winding parameters from one side to another side, right? So if a primary reactance transferred to secondary side, its value will become, you see the turns ratio 1 is to 100. As we are transferring to secondary, it will become 100 by 1 whole square into what is the primary reactance? 5. How much is this? 100 square, that is 10 power 4. It will become 50 kilo ohm. 50 kilo ohm. Okay, so this is inductive reactance, guys. But already there is a capacitive reactance and there is a resistance. Now we can draw equivalent circuit. So let me go to the note page so that it will be easy for us to draw. Yes, so I just transferred this reactance to the secondary side. So what is the total circuit now? If a 10 volt goes to the secondary side, it will become 1000 volt. Inductive reactance become 50 kilo ohm, right? 50 kilo ohm. But there is a capacitive reactance. We know capacitive reactance means it is minus j 20 kilo ohm, and the resistance finally, which is 40 kilo ohm. 40 kilo ohm. Am I correct? So see, this is inductive reactance, this is capacitive reactance. What will be the effective reactance if I combine both of them? That will become J30 ohm, correct? 50 minus 20, that is J30 ohm. Now what is the current in this loop? What is the current in this loop? Can I say current will be simply voltage divided by impedance? So let me go to the next page. So the secondary current will be equal to simply voltage divided by the loop impedance. What is the voltage referred to secondary? 1000 divided by loop impedance means it will be square root of real part square plus imaginary part square. I think this is 30 kilo ohm, right? This is 30 kilo ohm, correct? Okay, so the real part resistance is 40, reactance is 30. So it will become 40 square plus 30 square. Remember, this is a kilo ohm. All right. So this will become 1000 divided by square root of 40 square will become 1600. 30 square will become 900. Remember, this is kilo. That kilo goes to the numerator. Can I say this k and 1000 will cancel? Yes. So what will be the final answer? It will be 1 by square root of 1600 plus 900. It will be 2500. Okay, so I think it is 1 by 50. Is it? 1 by 50 means 0.02 ampere. So that is the amount of current that will be passing through secondary side of the transformer. So we will go back to the question paper. So the answer is 0.02 ampere. That is option C. So this is a simple question. So I just transferred primary side reactance to secondary side, and I just found the current voltage by impedance, correct? Okay. This is the solution. Okay. For any question, I request you to pause the video and try to answer on your own. Then if you did not get the answer, then just go through the video. Okay, to save the time, you can watch this video at 2x speed. Okay, so that you can save a lot of time. All right, now let's move to the second question in this series, electrical machines questions. Okay, just a moment. Okay. See, question number 2 is also from electrical machines only. You can read the problem. It is also from transformer subject. A 10 ohm resistive load is to be impedance matched by a transformer to a source with 400 ohm of internal resistance. What is the ratio of primary to secondary turns of the transformer? It's a simple question related to impedance matching of a transformer. Okay, see that the load resistance was 10 ohm. This 10 ohm must be matched with source resistance of 400 ohm. Can I say source resistance means it is on the primary side of the transformer? So primary side of the transformer has a source resistance. Let us say RS. This is equal to 400 ohm. All right. And then we have a transformer. This is the transformer. Now this transformer was connected to a load resistance. Let us say load resistance is RL. How much is the load resistance? 10 ohm. This load resistance was 10 ohm. Assume the turns ratio of the transformer was N1 is to N2. Now what the question they are asking, if I transfer this load resistance to the source side, it must be exactly equal to the source resistance 400 ohm. Then only I can say the load impedance was matched to source impedance. Okay, so what I need to do, transfer the load resistance to the primary side and it must be equal to source impedance. Okay, we just solved one problem, right, related to transferring of parameters from one side to another side. In a similar manner, if I transfer this load resistance to the primary side, can I say it will become RL dash? Now that RL dash value must be equal to 400 ohm. That's all. In order to do that, what must be this turns ratio? First of all, what is the formula for RL dash? I will try to solve here itself. Okay, I don't have space. I'll go to the note page. Yes. What is the formula for RL dash? RL dash, as we are transferring to primary side, it will become N1 by N2 whole square times of RL. Now can I say that must be equal to the source impedance, which is equal to 400 ohm? Yes. So that must be equal to source impedance, which is equal to 400 ohm. So I don't know what is N1 by N2 ratio. N1 by N2 whole square into what is the load resistance? 10 ohm is equal to 400 ohm. So can I say 10 will cancel 40 times here. So therefore N1 by N2 whole square is equal to 40. So N1 by N2 is equal to square root of 40. Understand? So what is the square root of 40? That will be the answer. Okay. So let's go back to the question. Yes, load resistance is 10 ohm. Okay. Load resistance is 10 ohm. We transferred that 10 ohm to the source side and it must be equal to source impedance 400. Understand? So what is the ratio of primary to secondary turns ratio of the transformer? That is the question. Okay. What is the answer? So it was square root of 40. I think something is missed, right? A 10 ohm resistive load is to be impedance matched by a transformer to a source with 400 ohm of internal resistance. The ratio of primary to secondary turns ratio. I think this question has a mistake. The source resistance should not be 400, it must be 4000. This must be 4000. I think it is marks to all type question now. If it is 4000 ohm, what happens? You see. For example, if the source resistance is 4000 rather than 400, if it is 4000, what will happen? Here, 10 will cancel 400 times. Correct? If it is 400, then the answer will be square root of 400. If it is a square root of 400, then you will get 20. Okay, then the turns ratio N1 by N2 is equal to 20. Then only one of the option will satisfy. What is that option? Option D. If the source resistance is 400 ohm, definitely the answer must be square root of 40. Square root of 40 is not available in the options. See, we got the answer square root of 40 initially. If it is a square root of 40, the answer should be 6.5, 6.6, something like that. But that option is not available. So therefore, the answer will be 20, but that is possible only when source impedance is 4000 ohm or load impedance must be 10 ohm. Sorry, 1 ohm rather than 10. load impedance must be 1 or source impedance must be 400. Any one thing must be satisfied, otherwise the option will not match. Okay, so anybody who wrote the paper, you can raise this question. Okay, all right, the options are not matching. It must be either 4000 or it must be 1 more. Then only this 20 option will satisfy. Clear? All right. This is question number 2. Right. Now, next question number 3 is also from transformer subject only. Yes, read the problem. Which of the following connection of a transformer will give the highest secondary line voltage? Yes, highest secondary line voltage. It's a direct question. Delta star is the correct answer. Delta star connection can offer the highest secondary line voltage. If you want, I will try to prove it. To prove that, let me consider we have different types of transformer connections. Let's say delta delta, we have star star, and we have delta star, and we have star delta. These are the four possible connections, right? And assume that all these connections are designed with 1:1 turns ratio, for example. That means ideal designs. Every transformer has the same turns ratio because nothing was given. Now, on the input side, let us say input line voltage. Here I am taking. I will take output line voltage here. I will take output line voltage here. Okay, right. Now, let us say for a delta delta transformer, if I give an input line voltage of 1 volt, how much output line voltage I can expect? Because remember, turns ratio will always represent phase voltage ratio or line voltage ratio. Yes, turns ratio is always a phase voltage ratio. If input line voltage was 1 volt, what is the input phase voltage? Also 1 volt only, because in delta line voltage and phase voltage both are equal. If input phase voltage is 1, output phase voltage is also 1 because it is a 1:1 ratio transformer. If output phase voltage is 1, what is output line voltage is also 1 volt only, because the phase voltage and line voltage both are equal. Next, let us consider a star by star transformer. Let us give input line voltage of 1 volt. If input line voltage is 1 volt, what will be the phase voltage? 1 by root 3. If input phase is 1 by root 3, what is output phase also according to turns ratio? 1 by root 3. If phase voltage is 1 by root 3, what is the line voltage? That will also becomes 1 volt. Clear? Next, let us consider a delta star transformer. Let me give an input line voltage of 1 volt. If input line voltage is 1, what is the input phase voltage? 1 only, because it is a delta. Line and phase both are same. If input phase voltage is 1, what is output phase voltage? Also 1, because it is 1:1 ratio. If output phase voltage is 1, because it is star, guys. In star, if phase voltage is 1 volt, what will be the line voltage? Root 3 volt. Okay, that means 1.732 volt, because line voltage will be root 3 times of phase voltage. Let's come to the last connection. Star delta. If input line voltage is 1, what will be the input phase voltage? Will be 1 by root 3. If input phase voltage is 1 by root 3, what is output phase voltage? Also 1 by root 3. If output phase voltage is 1 by root 3, can I say output line voltage also 1 by root 3 only? Because it is delta. Phase voltage and line voltage both are same. 1 by root 3 means what? 0.577. Therefore, look at this tabular column and tell me, every transformer has a same turns ratio. For every transformer, I am giving the same input line voltage, but which connection offers the highest output line voltage? Yes, you can understand the third one, delta star connection. Look at the output voltage, 1.732. That is the highest output voltage. For example, if the question is, which of the following connection offers lowest output line voltage, then the answer must be the fourth one. Star delta will offer lowest output line voltage. This is when every transformer was designed with the same turns ratio. Remember that. Okay. So the answer is delta star in this question. It is delta star. All right. This is question number 2. Sorry, question number 3, right? Next, question number 4 is also from electrical machines only. Let us see. Question number 4. In induction motor, if air gap is increased, what will happen? In induction motor, if air gap increases, what will happen? Speed will reduce, power factor will reduce, efficiency will improve, speed will increase. Remember, air gap length between stator and rotor of an induction motor, it will affect the magnitude of magnetizing current. I hope most of you might have idea about magnetizing current. Magnetizing current. What is magnetizing current? It is the component of current drawn by induction motor to establish rated flux in the air gap of the machine. And induction motor, magnetizing current is always directly proportional to the length of air gap. There will be a derivation to prove this. Okay, if you want, I can do that derivation also. Okay, what is the formula? Let's see. I hope most of you know about flux, MMF and reluctance relation, right? What is the formula for flux? Flux is equal to MMF divided by reluctance of air gap. What is mean by MMF? MMF is nothing but number of turns into current, and this current is nothing but magnetizing current divided by reluctance of air gap. Because this magnetizing current will create this magnetic flux. And if you cross multiply this relation, flux into reluctance of air gap is equal to number of turns into magnetizing current. What is the formula for air gap reluctance? Yes, length of the air gap by mu into cross-sectional area of the machine is equal to number of turns into magnetizing current. Now, according to this relation, yes, you tell me what is the relation between magnetizing current and air gap length? Assume remaining all parameters are rated values and we are maintaining those rated values constant. Therefore, the relation between magnetizing current and air gap length is directly proportional. So, therefore, magnetizing current is directly proportional to length of the air gap. This is all to create rated flux, guys. In order to create rated flux, that means we are keeping flux as a constant value. And then we are trying to develop a relation between magnetizing current and air gap length. Yes, it is a direct proportionality. Now tell me what happens if air gap length increases between stator and rotor. If air gap length increases, automatically the magnetizing current drawn by motor will increase. And we all know that magnetizing current is a purely reactive component. Magnetizing current is a purely reactive component and it will lag the supply voltage by 90 degrees. Okay, magnetizing current will lag the supply voltage by 90 degrees. And when I say reactive component increases, automatically power factor will be reduced. Therefore, what is a power factor formula? Power factor of any circuit is active power P divided by root over P square plus Q square. And when I say magnetizing current is reactive component, what will happen if reactive component increases? Power factor will be reduced. Okay, therefore, induction motor will operate at very poor power factor. That's why try to maintain air gap as less as possible. Okay, if air gap length is less, magnetizing current is less. If magnetizing current is less, reactive component is less. If reactive component is less, power factor will increase. That means the motor will operate at better power factor. Okay, so the point is very simple. Try to reduce the air gap length between stator and rotor. Okay, but the question is what happens if air gap length increases? So the answer will be power factor will be reduced. So do we have any relation between speed and air gap length? No. Speed will never depend upon air gap length, guys. It will always depend upon the load torque. Load torque will decide what is the speed of the induction motor. For example, if load is not connected, NR is almost near to NS. If load is increased, rotor speed will decrease. So load will decide what is the speed of the motor. Air gap will never decide. Okay, therefore option A and option D were wrong. Next, efficiency will have a relation, guys. This is a wrong answer. Why? Because actual answer is efficiency will reduce. Okay. If, for example, if efficiency reduces, if they say efficiency reduces, then it is a correct statement. But they said efficiency will improve. First of all, why efficiency will reduce? You come back to the discussion. Whenever air gap length increases, magnetizing current drawn by induction motor will increase, correct? If a magnetizing current increases, what is the disadvantage if current increases in any motor? Whatever current is increased, can I say it will create more copper loss in the machine? Copper loss will also increase. If copper loss increases, efficiency will obviously decrease. Whenever loss increases, efficiency will be definitely decreased. Therefore, correct answer is efficiency reduces, but they said efficiency will improve. Okay, that is a wrong statement. So the only correct statement was power factor will reduce. Okay, that is the correct statement. All right. This is question number 4. Next. Question number 5 is also from electrical machines only. This is also from induction motor subject. Okay, I request everybody, please pause the video and try to answer this question. If you did not get the answer, please let me know. This is a question from cogging and crawling phenomena of induction motor. Okay, presence of dominant 7th harmonic in the winding distribution of 3-phase 6-pole 50 Hz induction motor may cause motor to crawl at a speed of about how much RPM? Okay, so this crawling is what we generally call it as asynchronous crawling. Okay, asynchronous crawling. Yes, we know asynchronous crawling is mainly due to two harmonics. One is dominant 5th harmonic, another one is dominant 7th harmonic. Dominant 5th harmonic will create asynchronous crawling during reverse motoring mode. Dominant 7th harmonic will create asynchronous crawling in the forward motoring mode. And the crawling will generally occur at a speed Nr is near to Ns by 7 RPM. Generally, rotor must reach near to Ns RPM, but because of the crawling phenomena, rotor failed to reach its rated speed and it will find a new steady state at a speed very near to Ns by 7 RPM. So in order to understand, let us try to draw the characteristics of 3-phase induction motor. For example, if I take a speed on x-axis and a torque on y-axis. Okay, for example, if harmonics are neglected, if harmonics are neglected, then what is the only harmonic available? Fundamental harmonic only. And this is the torque speed characteristics of a 3-phase induction motor due to fundamental harmonic. But what if 7th harmonic is available? 7th harmonic also will create an extra electromagnetic torque like this. Okay, so this is the torque due to 7th harmonic. This is the torque due to fundamental harmonic, that is the first harmonic. Then what about the resultant torque? Resultant torque will be combination of these two. So when I draw the combination of these two, I will get a new graph something like this. Just see. So we will get a new graph. Yes, something like this. This is exactly Ns by 7. Okay, all right. So if you wanted to know what is the only fundamental harmonic, yes, this blue color curve is fundamental harmonic torque only, but the black color curve is, it is a combination of both fundamental and 7th harmonic torques. Now, what if there is a load connected to this induction motor? Imagine this is the load torque. Okay, so the moment when the load is connected, for example, if only fundamental torque is available, okay, only blue color curve is available, then the steady state will come exactly at this particular point. And this point is very near to Ns RPM. But due to the 7th harmonic torque, this extra bump is created, am I right? This black colored line. Therefore, the steady state will come at this particular point. This is the new speed at which steady state will come. And are you understanding, this new speed is just more than Ns by 7 RPM? Just more than, okay, very near to Ns by 7 RPM. So therefore, the crawling will come at a speed slightly more than Ns by 7 RPM. First of all, what is Ns in this question? Ns is equal to 120 F by P. I think in the given question, just a moment. Yes, frequency was 50 Hz and the number of poles were 6. Therefore, Ns is equal to 120 F by P. So 120 into frequency was 50, number of poles were 6. This is 1000 RPM. If Ns is 1000 RPM, then what about Ns by 7? That is 1000 by 7. 1000 by 7 means 1 time 30 will be there, 4 times 28, another 20. So approximately 143 RPM, correct? I think 142 point change something will come. So near to 143 RPM. So therefore, the crawling will come at a speed very near to 143 RPM. This is the correct answer. This is due to fifth harmonic, and this is asynchronous crawling. Okay. There is another type of crawling also. We call it as a synchronous crawling that you will generally study in a induction machines course. Okay. Yes. So this is electrical machines question. 5 questions so far. Now let's see question number 6. This is also from electrical machines only, a single phase induction motor question. I request everybody please read the question. At starting, the winding of a 230 volt 50 Hz split phase induction motor have the following parameters: main winding and starting winding. Current in the main winding of the induction motor is how much? See, the question is about starting. We know in a single phase induction motors, 2 types of windings will be available in the stator part of the machine. One is main winding. Okay, just let me draw it. So yes, one is main winding, another one is auxiliary winding. This auxiliary winding is also known as starting winding of induction motor. Both will be connected in parallel with each other, and sometimes we will connect a capacitor in series with auxiliary winding in order to start the motor. Then we call it as a capacitor start induction motor. Okay, but they are asking what is the current passing through main winding only. What is the question? The current passing through main winding. Okay, so let me try to draw the circuit diagram first. Okay, so if it is a single phase transformer, 2 windings will be available. So this is the main winding, resistance of the main winding, leakage reactance of the main winding, and then auxiliary winding will be connected here, resistance of the auxiliary winding, leakage reactance of the auxiliary winding, and as I said, auxiliary winding will be generally connected in series with a capacitor. We call it as start capacitor of the induction motor, and here we have the supply voltage. This is the exact circuit diagram of a single phase induction motor at the time of starting. Now what they are asking, what is the current passing through this main winding? That is the question. So as the both are connected in parallel, can I say current passing through main winding is simply supply voltage divided by root over main winding resistance square plus main winding reactance square. There is no capacitance in main winding. Remember, capacitor will be added in series with auxiliary winding. Auxiliary winding is known as starting winding of induction motor. Okay, so now what is the supply voltage given in the question paper? Just so supply voltage was 230 volt. It is clearly mentioned. Main winding resistance 3, reactance 4. So this will be 230 divided by main winding resistance is 3 ohm, reactance is 4 ohm. So is it not 230 divided by 5? Okay, 3 square 9, 4 square 16, under root it will be 5. So 230 divided by 5. So it is 4 times and 6 times. Okay, so 46 ampere will be the current drawn by the main winding. I think option D. This is correct option. So that is the current drawn by main winding at the time of starting. It's a simple question. All right. Fine. So this is also electrical machines question. So far we solved 6 questions. Okay. Right. Let's move to the next question. Next question number. Question number 8. Question number 7. Sorry. This is also from electrical machines. This is from synchronous machine subject. So request everybody, please read the problem first. It's a simple question. A synchronous motor with negligible armature resistance runs at a load angle of 20 degrees at the rated frequency. If a supply frequency increases by 10%, keeping other parameters constant, what will be the new load angle? Okay, most important observation is supply frequency increases by 10%. Okay, supply frequency increases by 10%, keeping other parameters constant. This is very important. What is mean by other parameters constant? That means they increased supply frequency by 10%, but there is no change in supply voltage, no change in load power, no change in field excitation, because these are the important variable parameters, right? In generally in synchronous motor or synchronous generator, you can change excitation, you can change torque input or torque output, you can change supply voltage or frequency, but here only frequency changes increased by 10%, no change in other parameters. No change in other parameters means supply voltage will be constant. Let me go to the next page. So they said frequency increases by 10%, no change in other parameters. That means terminal voltage is constant. Field excitation, okay, field current indirectly, field excitation is constant. Okay, no change in load power. Load power is also constant. These are the active points. Okay. Now, the moment I say load power is not variable, it is constant. What is the formula for power when armature resistance is neglected? EF into VT by XS into sine delta. Correct? This is the formula for active power. Here, active power P is constant. P is a constant value. Terminal voltage is a constant value. What about EF? Does EF will change or not? Yes, we know EF is nothing but field induced EMF. What is the formula for field induced EMF of a synchronous motor or synchronous generator? It is 4.44 into field flux into frequency, number of turns into winding factor. That is a formula. No change in field excitation. Field flux is constant. But frequency increases by 10%, right? As frequency increases by 10%, induced EMF will also increase by 10%. Definitely. Okay, so induced EMF increases by 10%. Next, what about XS? XS is synchronous reactance. You can write XS as 2 pi F into L, where L is the inductance of the machine. So when frequency increases by 10%, XS will also increase by 10%. So this XS is also increases by 10%. See, numerator EF increases by 10%, denominator XS also increases by 10%. That means this ratio will be constant. If EF by X ratio is constant, indirectly sine delta remains constant. Okay, if you want more explanation, so power in the first case and power in the second case must be equal because power is constant. What is the power in the first case? EF into VT by XS into sine delta 1. Let us say this is the first case load angle. Must be equal to 1.1 EF into VT by 1.1 XS into sine delta 2. Why I multiplied with 1.1? Because EF increases by 10%. Reactance also increases by 10%. So what will happen now? Yes. So this EF, VT, XS will cancel on left side and right side. 1.1, 1.1 will cancel. So we are getting sine delta 1 is equal to sine delta 2. Indirectly, the load angle does not modify. So the answer is same load angle once again. Same load angle once again. Same load angle means how much? 20 degrees. Okay, so the answer is 20 degrees. Okay, 4 options are there: 18, 16, 20, 22. So the answer is 20 degrees. Okay, load angle does not change. Remember, only frequency increases by 10%. Remaining parameters are constants. Remaining parameters means supply terminal voltage is constant, load power is constant, field excitation is also constant. Okay, yes. That is question number 7. Next, we have a question number 8 that is also from electrical machines subject only. Look at that. Question number 8. Read this problem. An induction motor and a synchronous motor are connected to a common bus bar. To operate the bus at unity power factor, the synchronous motor should be normally excited, under excited, over excited, disconnected from the bus. This is the question. Okay. So the point is, an induction motor and a synchronous motor both are operating in parallel. Okay. So imagine this is a bus bar. I am connecting an induction motor to this. I am also connecting a synchronous motor to this. This is the bus bar. But I wanted to operate the overall set at unity power factor. To operate any set at unity power factor, the overall reactive power demand must be 0. But we know induction motor is a machine which always absorbs reactive power. Okay. Now, what if our synchronous motor generates the same amount of reactive power to the bus bar? For example, induction motor absorbs 1 per unit reactive power. What if our synchronous motor generates 1 per unit reactive power? Then the overall reactive power from the bus bar becomes 0 and the system will be at unity power factor. And so, in order to operate the system at unity power factor, our synchronous machine must generate reactive power. Synchronous motor will generate reactive power only when the motor is operated at over-excitation condition. That is also known as synchronous condenser case. So, the answer is over-excitation. The answer is over-excited. So, simple question, one-step solution. Remember, induction motor will always absorb reactive power. So, to compensate this absorption, our synchronous motor must generate reactive power. Exactly same amount. So that the overall power factor becomes unity. Okay. This application is known as a synchronous condenser application that will improve the power factors of the loads. Okay. And generating reactive power by a synchronous motor is possible only when the motor is overexcited. Clear? So the answer is overexcited. So the first 8 questions came from electrical machines subject only. And now we have next machines question number 22. See, these are all power systems questions later. Let me go to question number 22. Just a moment. These are all power system and power electronics questions. Next we have question number 22. Yes. Let me zoom in. Okay. This is another electrical machines question, and this question is from DC generator. Request all of you, please read that question. An 8-pole lap-wound DC shunt generator is supplying 295 ampere to a load. The field current of the generator is 5 ampere. What is the current per each parallel path is the question. They say it is a shunt generator and it is supplying 295 ampere to the load. Okay, and it is 8-pole lap connected machine. First of all, as it is a shunt generator, can I draw the circuit diagram? In a shunt generator, this is the armature. Field winding will be connected in shunt with armature, and the load will be connected in parallel with armature. This is the load resistance. This is the field resistance. Important thing, what is the current that machine is delivering, supplying to the load? 295 ampere. This is 295 ampere. And the field was taking 5 ampere. The field was taking 5 ampere. Therefore, if you apply the KCL equation, you can easily understand the armature current will be 295 plus 5. Overall, 300 ampere. Armature current was 300 ampere. But the question is to find out armature current or current in each parallel path. Yes, the current in each parallel path is the question. We know current in each parallel path in DC machine is represented with the letter small I, that is IA divided by A. That is the current in each parallel path, where A represents number of parallel paths. Yes, how many parallel paths will be there in this machine? The machine is lap wounded with 8 poles. We know in a lap connection, number of parallel paths are equal to number of poles. As there are 8 poles, indirectly 8 parallel paths. Therefore, the answer is 300 divided by 8. 300 divided by 8. So that will be the answer. Okay, you can easily find out 300 divided by 10 is 30. 8 means more than 30. So the answer will be 37.5. Correct? 37.5. Just very simple question. In one step, you can answer this question. Okay. So it's a shunt generator. Be very clear with that. 300 by 8. 300 by 10 is 30. 300 by 8 means more than 30. So 37.5 ampere current will flow through each parallel path. That is question number 22. Next, question number 23 is also from electrical machines only. This is also from DC machines subject. Okay. Okay, request all of you, please read this problem. A DC shunt motor takes 5 ampere at 100 volt when running at light load. Light load can also be treated as no load. Shunt field resistance was 50 ohm. Armature resistance was 0.2 ohm. What is the driving power? Okay, what is the driving power they are asking? So first of all, it is a shunt motor. So as it is a shunt motor, I can draw a circuit diagram. Earlier it was a shunt generator, right? This is a shunt motor. Just a moment. Okay, so I'm trying to draw here. This is the armature part of a shunt motor. This is the field winding. Here we have the supply. Okay, yes. From the supply, how much current the motor is taking? 5 ampere. 5 ampere is the current drawn by the motor at a supply voltage of 100 volt. Out of that 5 ampere, can I say some current will go to the field circuit? What is the formula for field current? Field current is equal to supply voltage divided by field resistance, because it's a shunt motor. Supply voltage was 100, field resistance was 50, correct? Field resistance is given 50. So it was 2 ampere. So 2 ampere will go to field circuit. So out of the 5 ampere supply current, if 2 ampere goes to field, then how much will go to armature? Obviously, remaining 3 ampere will go. So armature current will be 3 ampere. So let me use the note. So supply voltage was 100 volt. Field current was 2 ampere. Armature current was 3 ampere. What is the armature resistance of the machine? Armature resistance was 0.2 ohm, correct? Armature resistance is 0.2 ohm. They are asking power developed by the machine. Driving power, also known as power developed by the machine. So the first thing is, I would like to calculate back EMF of this motor. What is the formula for back EMF? Vt minus Ia into Ra. Vt was 100, armature current was 3, armature resistance was 0.2. So it was 100 minus 0.6, it was 99.4 volt. This is back EMF of the motor. Now what is the formula for power developed by the motor? Power developed by the motor is simply EB into Ia. So EB was 99.4, Ia was 3 ampere, it is less than 300 watt. Okay, for example, if you treat 99.4 as 100, 100 into 3 is 300 watt. So 99.4 into 3 is less than 300 watt. Okay, so let's see the answer. Just a moment. So it will be 298 watt, right? This 298 would be the correct answer. Okay, simple question. Request everybody, please recheck the calculation. 99.4 into 3. Yes. 298 watt. Okay. So this is the power, and this 298 watt power is utilized to drive the motor. Okay. So that is what. Just EB into Ia. Simple question. Next. Question number 24 is also from electrical machines only. Let's go through that. Okay, this is again a question from transformer subject. All of you please read this problem. Just a moment. Yeah. All of you please pause the video and read the problem first. It is easy question, we can answer it. A three-phase 50 Hz transformer has a delta connected primary and a star connected secondary. The line voltage being 22 kV and 400 volt respectively. Secondary has a star connected balanced load at 0.8 power factor lagging. The line current on the primary side is 5 ampere. What is the secondary side phase current would be? See, very clearly they said it is a delta connected primary, star connected secondary, right? Delta connected primary, star connected secondary. Primary side line voltage was 22 kV, secondary side line voltage was 400 volt. Primary side line current is 5 ampere, then what is the secondary side phase current is the question. So let me try to draw a diagram. So let me open the note. Primary is delta connected, guys. Let's say this is the primary side delta connection. Clear? Secondary is a star connection. Secondary is a star connection. Okay. Now the point is primary side line voltage was 22 kV. Secondary side line voltage was 400 volt. Yes, primary side line current was given. Let us say this is I1. Okay. This is V1. Let me open the question paper. Yes, primary side line current was 5 ampere. What is the secondary side phase current is the question. This is 5 ampere. Secondary side phase current they are asking. First we will try to find out line current on the secondary, because we know in a star connection line current and phase current will be same. But as it is a transformer, we know in a transformer primary side volt ampere power is equal to secondary side volt ampere power. What is the formula for primary side volt ampere power? Root 3 V1 I1 is equal to root 3 V2 I2. Okay, so root 3 into what is V1? Indirectly the line voltage 22,000 into I1 5 ampere is equal to root 3 into V2 was 400, I2 was unknown. So root 3 will cancel. I will go to the next page. So 22,000 into 5 is equal to 400 into I2. Two zeros will cancel here. Therefore, I2 will be equal to 220 into 5 divided by 4. Okay, I think 4 will cancel in 220. So 5 times it will be 20. I think 55 times into 5 by 1. Correct or not? Just recheck that. 55 into 4, 220, correct. So the answer will be 55 into 5. This will be secondary side line current, guys. If you know secondary side line current, can I say secondary side phase current will also be same, because secondary is a star. In a star, phase current and line current both will be same, right? 50 into 5 is 2500. So it is 2525 ampere probably. Yes or not? 2525 ampere. If I go through the question paper, yes, 2000. Just a moment, guys. I think the options were not available. Did I made any mistake? I think my calculation has a mistake. It is 555 into 5, right? It's not 2500, guys. Just a moment. Where is it? $55 into 5. 50 into 5 is 250. 250 plus 25, 275, correct. Yes, be clear with calculations. Apology for the mistake. Yes, it was 275 ampere. Okay. So simple rule. See, one additional data that I am not using here. What is that? Power factor. They said secondary side has a load with 0.8 power factor lagging, but I don't require power factor at all because my requirement is to calculate the current magnitude. To calculate the current magnitude, just equate the volt ampere powers. Volt ampere power does not have a power factor relation, right or not? Okay. That's why no need to use that additional information given power factor. So just use the volt ampere power relation, you'll get the current magnitude, right? This is question number 24, right? 24 is a machine. Next, 26th question is a machine's question. This is a control systems question, question 25. 26 is again a machine's question. Read the problem. A three-phase alternator generates an open circuit phase voltage of 4 kV when excitation current is 50 ampere. The short circuit current for the same excitation is 800 ampere. What is synchronous reactance per phase? So the question is about calculating synchronous reactance. So we know synchronous reactance in an alternator is the ratio between open circuit terminal voltage to short circuit armature current. The important thing is both must be measured at same field current. Okay, that means if open circuit voltage was measured at a field current of 50 ampere, short circuit current should also be measured at same field current. And remember, only phase quantities we have to select. I think already the open circuit voltage was 4 kV per phase, right? It is a phase voltage, so need not to worry. This will be 4 kV, that is 4000 divided by what is a short circuit current? 800 ampere at the same excitation. That is important. At the same field current, directly 800 ampere. Two zeros will cancel. 40 by 8, it will be 5 ohms per phase. So the answer is 5 ohm. Simple question. But sometimes what happens is they will measure open circuit voltage at 50 ampere field current and they will measure short circuit current at 100 ampere field current or maybe 25 ampere field current. Then you have to convert the data, okay? Because short circuit characteristics are straight line passing through origin. If you know short circuit current at 100 ampere field current, you can easily find out short circuit current at 50 ampere field current also. Okay, need not to worry. So the answer is 5 ohm per phase. That is the value of synchronous reactance. This is a machine's question. Next. Next, question number 27 is also machine's question only. When load on an alternator is increased, the terminal voltage increases if the load power factor is which type? They said very clearly, load on alternator is increased. When I say load increases indirectly, the load power increases indirectly. When the load on an alternator increases, the terminal voltage increases. Okay, so load increases, then terminal voltage should also increase. See, point is, whenever load increases in power system, what is meant by load increases? We are connecting extra load in parallel with existing load. So whenever load increases, automatically the current drawn by the load will also increase, right? Indirectly, armature current also increases. When armature current increases, they said the terminal voltage also increases. Now the terminal voltage will also increase. When this is going to happen? That is the question. Okay, can I say this is possible only with leading power factor case? Why? Because when power factor is leading, what is the nature of armature reaction? For leading power factors, the nature of armature reaction is magnetizing in nature. Magnetizing nature. Am I right? If it is lagging power factor, armature reaction is demagnetizing. Because it is magnetizing in nature, resultant flux will be increased. Whenever armature current increases, armature flux will be increased. And as it is magnetizing the field flux, resultant flux will also increase. If resultant flux increases, the resultant voltage will be increased. That is how the terminal voltage increases. Therefore, the answer is a leading power factor. Okay, that means armature reaction is magnetizing. If it is magnetizing, then only flux and terminal voltage both will increase. Understand? Okay, simple question. This is question number 27, that is from electrical machine. Next, Question number 28 is also from electrical machines only. Request everybody, please read the problem. Pause the video for a moment, read the problem and try to answer that. Right? This is a question from alternators. When n number of alternators are operating in parallel, the power factor at which each operates is determined by what? So, very simple question. Many number of alternators are connected in parallel. Okay. Yes, it's a parallel operation of alternators. Just a moment, guys. Okay. See, when number of alternators are operating in parallel, imagine this is the first alternator, second alternator, third alternator, like that. Many alternators are connected in parallel. Imagine they are together connected to a common bus bar or maybe feeding a common load, something like that. Okay. So now the point is how to control the power factor of each and individual alternator. Remember, power factor is always active power divided by root over active power square plus reactive power square. This is the formula to determine the power factor of any alternator. For example, if I wanted to find out the power factor of this third alternator, let's say 1, 2, 3, like that n alternators are there. I wanted to calculate what is the power factor at which this third alternator is particularly operating. Then I have to find out what is the active power the third alternator was generating and what is the reactive power the third alternator is generating. If I know active power and reactive power of this third alternator specifically, then I can easily identify what is the power factor at which third alternator is operating. For example, if reactive power is positive, then it will be lagging power factor. If reactive power is negative, that will be leading power factor. Okay, if Q is positive, that is lagging power factor. If Q is negative, that is leading power factor. And if Q is 0, then unity power factor. This is what we know in alternators. Therefore, to control the power factor of any alternator, you have two choices. You can control the power factor either by controlling this P value or by controlling this Q value. Okay, but how to control whether it is lagging or leading or unity power factor, that you can decide based on the sign of the reactive power. Reactive power is positive, that means machine was generating reactive power, then it is lagging power factor. Reactive power was negative, that means the machine was absorbing reactive power, then this is leading power factor. Therefore, to control the power factor, we have two choices. One is by controlling active power, another one is by controlling reactive power. How to control active power? That is there in the question paper. How to control active power? That is by using driving torque of the prime mover. What is meant by driving torque of the prime mover? Indirectly controlling the active power only. That is a prime mover input. We also call it a steam input. How to control the reactive power? By controlling its field excitation. Both are available in options. This will control the active power of the alternator. This will control the reactive power of the alternator. Whether you control active power or reactive power, power factor will change. Then what option I have to select here? Because I have a choice to select only one option. Then the most preferable answer is field excitation. Why? Because controlling the prime mover input is primarily to control active power but not to control power factor. Remember that. To control the active power, we will control prime mover input. Okay, active power is the first priority. Then automatically power factor will change. But if I ask you, see, you are an engineer in a power plant. You got an order that, sir, your power plant was generating 100 megawatt today. Please increase that 100 megawatt to 120 megawatt because we have more load demand. Then what you will do? To increase 100 megawatt to 120 megawatt, you will go to turbine governor system. You increase the steam input. That's all. The moment when steam input increases, automatically active power will increase from 100 megawatt to 120 megawatt. Okay, that is the order you got. But the moment you change the steam input, active power changes. Whenever active power changes, automatically power factor changes. Because what is the order you got from the power grid? Increase the active power generation. They are not asking you to control the power factor. That is secondary thing that is happening. Primary thing is you are increasing the active power. Automatically power factor will change. That is secondary thing. But for example, you got an order from the power grid. Sir, you are generating 100 megawatt at 0.8 lagging power factor. Please control your power factor to unity. You got an order. That is order you got from the power grid. So what do you do now? Will you increase the steam input or will you decrease the steam input? No. If I increase the steam input or decrease the steam input, active power will change. But the order I got from the power grid is just to change the power factor, not to change the steam input or not to change the active power. I just wanted to change power factor only. If I wanted to change only power factor, then change excitation. Changing the excitation will change reactive power. Active power remains constant because I am not changing steam input. Active power remains constant. Only reactive power will change and power factor will automatically change. Therefore, steam input will be varied only to change active power. Field excitation will be varied only to change power factor. So the best answer is field excitation. Got it? Yes. Yes, that is machine's question again. Next, question number 42. Next, we have few power electronics and power systems questions. This is overcurrent relay. Next, we have 42 questions. Second, question number 42. Yes, this is a question from DC motors again. Go through question number 42. Request everybody to read the problem. A series motor has an armature resistance of 1 ohm. It runs at 800 RPM at 200 volt with a current of 15 ampere. What is the speed at which it will run when connected in series with 10 ohm resistance and taking the same armature current at the same supply voltage? Remember, initially machine was rotating at 800 RPM, drawing 15 ampere current. Next time, an extra resistance was added in series, 10 ohm resistance is added. What is the new speed with the same armature current? Same armature current. So very simple, there are two cases in the problem. First case, before adding the resistance. Second case, after adding the resistance. Okay, let me note down the data. 200 volt supply voltage. Total resistance of the machine was 1 ohm, rotating at 800 RPM and current is 15 ampere. What is this? Okay, so case number 1. Case number 1 means before adding extra resistance. Remember, this is a series motor. This is a series motor. Terminal voltage was 200 volt, drawing an armature current of, forgot it. What is armature current? 15 ampere, right? 15 ampere. With a resistance of 1 ohm and a speed of 800 RPM. This is the total resistance of the machine, let's say RP. Now, what my first point, find out back EMF. What is the formula for back EMF of the motor? I am writing suffix 1 to understand this is the first case. Back EMF is equal to Vt minus armature current into total resistance of the machine. Vt was 200 volt, armature current was 15 ampere, total resistance is 1 ohm, so it was 185 volt. This is the back EMF. Now in the next case, what was happened? Case number 2, this is after adding external resistance. Terminal voltage will be same, 200 volt. Armature current is also same. They said very clearly in the problem itself, yes, same armature current, right? If you look at this last line, same current, the current is the same, okay? Same armature current, but this time the resistance is total resistance of the machine plus extra resistance. 1 ohm plus how much extra resistance is added? 10 ohm. Overall it is 11 ohm. What is the new speed of the motor? To find out the new speed, first I need to find out the new back EMF. Back EMF is Vt minus Ia into now total resistance of the machine plus extra resistance we added in series. So it was 200 volt minus armature current was 15, total resistance was 11. Okay, so it is 200 minus 150, 165. If 165 is removed, then 35 volt will be the new back, very low back EMF. Once I know the back EMF value, now I can find out the new speed. What is the formula for back EMF? We know back EMF is equal to Ka phi into omega. And remember, it is a series motor. Therefore, flux is proportional to armature current, right? In series motor, armature current and field current both are same. And in the question, armature current was changing or constant? Constant. In both cases, same armature current, right? As armature current was constant, flux is also a constant value. If flux is a constant value, therefore, back EMF is only proportional to speed. So back EMF in the first case divided by back EMF in the second case is equal to N1 by N2. What is the back EMF in the first case? 185. 185. Back EMF in the second case 35. Speed in the first case 800 RPM. Speed in the second case is the question N2. So if I cross multiply, N2 is equal to 800 into 35 by 185. If it is a 30 by 180 approximately, it will be 1 by 6 times, right? 1 by 6 times. So approximately 800 by 6. Okay, you can choose the nearest answer. All right or not? 800 by 6. That means 400 by 3. 400 by 3 means more than 100 RPM. Approximately more than 100 RPM. So out of the available options, you can select an option which is more than 100 or near to 100. Okay, let's go back to the problem. I think 151 would have been the approximate answer. Okay, I'm not sure. I need to check the calculation. You also do it. Approximately, I did it. Okay, if you want exactly, you can cancel 7 times here. 5 will cancel 7 times here. Here, 3 times 15, 35, 7 times. It is 7 by 37. You can do it. Clear? So I'm approximately doing. If you do it exactly, you'll get the exact answer. Remember, it's a exam where calculator may not be involved. So try to solve without calculator only. All right. Yes. So the nearest answer will be 150. Just more than 100, guys. Okay. If I do it, approximate calculator, I don't know. You need not to do it like this. Okay. This 35, I will treat it as 30. 185, treat it as 180. Approximately, I'm doing. Okay. Then 30 will cancel 6 times. 800 by 6. 800 by 6 means 400 by 3. What is a 400 by 400? 400 by 3, more than 100. So the answer is more than 100. Okay, more than 100. So the options, look at the options. I have more than 100, 151 RPM. Clear? Next, we have question number 44, machines question. Just a moment, guys. Question number 44. Okay, question number 44, just read the problem. If one of the main line connected to induction motor is changed, then what will happen? See, the meaning of changed means, for example, an induction motor is excited with ABC sequence. This is the induction motor we have. It is excited with ABC sequence, for example. What if one of the line is changed? That means I connected B to this point and C to this point. That means sequence will modify, right? ABC sequence will next time change to ACB sequence. This is what I'm doing. Okay, if I change like that, even though supply is ABC, the sequence received by the motor will be ACB. We all know when sequence is reversed, machine will rotate in opposite direction. ABC sequence will rotate the machine in forward direction. ACB sequence will rotate the machine in opposite direction. So flux speed increases, that is wrong. Flux speed decreases, that is wrong. Flux speed remains the same, but direction is reversed. This is correct. First of all, what is meant by flux speed? Flux speed is nothing but a synchronous speed, guys. What is the formula for synchronous speed? 120 F by P. Therefore, flux speed will change only if you change supply frequency. In the question, they said frequency changes or only the sequence changes, only the sequence is modified. No change in the frequency. That's why flux speed remains the same. Flux speed remains the same, but the direction will reverse. Okay. Direction will reverse. So this is the correct answer. Even the last option is also wrong. Flux speed and direction remains unchanged. That is wrong. Speed is unchanged, but the direction will change, right? ABC sequence will rotate the field in forward direction. ACB sequence will rotate the same field in backward direction. Correct? That is question number 44. Next, question number 45, that is also a machines question only. Go through that. If a supply voltage of a three-phase induction motor is increased 2 times, then what happens to torque? To do that, I will write down the torque equation of an induction motor. In three-phase induction motor, the electromagnetic torque equation is 3 by omega s into E2 square divided by R2 by S whole square plus X2 square into R2 by S. This is the formula for electromagnetic torque at a given slip S. From this formula, you can write electromagnetic torque is from this E2 is the voltage, is proportional to square of the voltage. And in the question, they said voltage is increased by 2 times, correct? Voltage is increased by 2 times. If voltage increases by 2 times, can I say torque will increase by 2 square times, indirectly 4 times? So the answer is it will be increased to 4 times. Option C. Simple question. Torque is proportional to square of the voltage. If voltage is doubled, the torque will increase by 4 times. Next, question 46 is also from machines only. Go through it. Rotor current in a three-phase induction motor is inversely proportional to slip, directly proportional to slip, dependent on slip, root 3 times of slip. So that is the question. Rotor current in three-phase induction motor. So to answer that, I will try to draw the rotor equivalent circuit of induction motor. Rotor equivalent circuit. Okay. So if I draw that, we know rotor will have 2 parameters. One is effective resistance of the rotor, which is R2 by S. Another one is reactance X2. This is the rotor voltage E2. This is the rotor current I2. This is the equivalent circuit of induction motor at a slip S. Now from this, what is the rotor current I2 formula? This is E2 divided by root over R2 by S whole square plus X2 square. This is the exact formula for rotor current. But the point is, the magnitude of the current will definitely depend upon this resistive value as well as reactance value. I hope most of you know that. If you draw the torque speed characteristics of induction motor or torque slip characteristics of induction motor, this is how the characteristics looks like, right? This is the point where slip equal to 1, that is a starting point. This is the point where slip equal to 0, that is a synchronous speed. This is the point we call it as SMT, slip where maximum torque is created. I hope most of you have some idea that yes, in this non-linear zone, generally R2 by S will be very less compared to X2. But in this linear zone, R2 by S is much higher than X2. Why? Because in the linear zone where slip is near to 0, right? As slip was near to 0, this R2 by S ratio will be very high compared to X2. So I can write if R2 by S is very less compared to X2, then R2 by S whole square can be neglected. Therefore, rotor current equation becomes, see, if R2 by S whole square is neglected, can I say rotor current equation becomes E2 by X2? This is the first observation. This is in this non-linear zone, indirectly, okay? Non-linear zone. This is non-linear zone of the torque speed characteristics. But in the linear zone, what is observation? In the linear zone, R2 by S is much higher than X2, right? So second case, if R2 by S is much higher than X2, that is linear torque speed characteristics zone. As R2 by S is much higher, X2 square can be neglected in the equation. If X2 square is neglected, rotor current will become S into E2 by R2. See. So if X2 square is neglected, rotor current will become only R2 by S whole square will left. So S will go to the numerator. That means if it is non-linear zone, rotor current is independent of slip, right? It is almost independent of slip. There is no slip here. But in the linear zone, rotor current is dependent on slip and it is directly proportional to slip. So what are the options available with me? Rotor current is inversely proportional to slip. This never came into picture, right, or not? I have only two options. Either it is independent of slip or directly proportional to slip. I will go back here. See, this is where rotor current is directly proportional to slip. Correct? This is where rotor current is independent of slip. I2 is almost independent of slip. These are the only two possible options for me. Rotor current independent of slip, rotor current directly proportional to slip. But if I go to the options, rotor current is inversely proportional to slip, wrong answer. Yes, directly proportional to slip, possibility is there. Independent of slip, possibility is there. Root 3 times of slip, there is no possibility. Now the point is, two options I am getting. Directly proportional to slip, independent of slip. Which option I have to select? Because both are there here. Independent of slip, this is non-linear zone. Directly proportional to slip, this is linear zone. Now the point is, when both are available, I have to select only one option. Then I will select this linear zone only. Because we all know that induction motor will be stable only in this linear zone or non-linear zone. Yes, induction motor will be stable in the linear operating zone. In the linear operating zone, what is the relation between current and slip? Directly proportional. So therefore, my answer will be obviously directly proportional to slip. This is also correct, but that is in the non-linear zone, but non-linear zone is an unstable zone. So when I have something to select only one out of the two, I will be selecting the most preferable answer, which is stable operating zone. Stable operating zone means current will be directly proportional to slip. That is second option. A very important and intelligent question, right? Okay. For example, if the same question is given like this, which of the following options are correct? These are not four options, but these are four statements. Then second statement is correct, third statement is also correct. Got it? Yes. So for this, the most preferable answer will be second option. All right. Next, question number 47. This is also from electrical machines only. It's a numerical question. Request you to pause the video and just read the problem. Yes. A three-phase 16-pole alternator has a star-connected winding with 144 slots and 10 conductors per each slot. Consider KD 0.96, KP equal to 1. Flux per pole is 30 milliweber, sinusoidally distributed, and speed is 375 RPM. What is the line EMF of the machine? That is the question. Okay, so they are asking just EMF value of the machine. Yes, direct formula is there. What is the field induced EMF of the machine? Field induced EMF is equal to 4.44 into field flux, frequency, number of turns into winding factor. Remember, this is the voltage per phase. Here, the most important data is number of turns per phase. Turns per phase. It was not given directly in the problem. You see, in the problem, what they said, there are 144 slots in the problem. There are 144 slots. Every slot has 10 conductors. Therefore, overall conductors information is available. So first let us find out total conductors. Change the color. Yes, total conductors. is equal to 144 slots. Every slot has 10 conductors. Therefore, I must say total 1440 conductors are available. 1440 conductors are available. 1440 conductors means, can I say 720 turns? Because a turn will have two conductors. This is what is mean by a turn. A turn will have two conductors. So 1440 conductors means 720 turns. Total turns. But I need turns per phase. It's a three-phase machine, right? Let's go back to the question. Yes, it is a three-phase machine. Therefore, 720 by 3, how much it will be? It is 2 times 6, 4 times. 240 turns per phase. 240 turns per phase. Now I have turns per phase, remaining quantities are available. I can directly calculate the induced EMF. So induced EMF is equal to 4.44 into, what is the field flux given in the problem? 30 milliwebers, right? Field flux was 30 milliwebers. Milli means 10 power minus 3. Frequency was 50 hertz, right? Frequency was not given, guys, but speed and poles are given. I can find out frequency from that. What is the formula for frequency? Pn by 120. Poles are 16. Speed was 375. Correct? I hope you are following, right? 375 by 120. This will be 50 hertz. Because for 8 pole synchronous machine is 750, this will be 50 hertz. So frequency was a 50 hertz into number of turns we just calculated 240. kW means kp into kd. In the given problem, kp is 1, kd is 0.96. Okay, so you have to answer this without calculator. It's possible. Don't say it is impossible. It is possible because you have to take approximate calculations. How it is possible? You see that there are 3 zeros here. If you carefully see, 1, 2, 3. Can I say 3 zeros and 10 power minus 3 will cancel? And I am taking 4.44 approximately as 4. Let us reduce this and let us increase this to 1 so that I will get approximate value. So therefore, what is my next multiplication? This is 4 into 3 into 5 into 24 into 1. As I reduced one product, that's why I am increasing another product so that I will get approximate answer. So 4 into 3, 12. 12 into 5, 60. It is 60 into 24. Okay. 240 into 6. 200 into 6 is 1200. 240 into 6 is more than 1200. So just this is the phase voltage, guys. Remember, this is the phase voltage. Voltage per phase. 240 into 6. Okay, I'll go to the next page. So EF is equal to approximately 240 into 6. It is 1200 plus 6 times it is 200 into 6. It is 240. So 1440 volt per phase. But I think the answer we require is line voltage. What is the line voltage in star connection? Is it a star connection? Let's check that. Has a star connection, yes. Star connection means line voltage will be a root 3 times of phase voltage. So root 3 into 1440. What is root 3? 1.732 into 1440. See, 1.732 is approximately 2. For example, if this is 2, this would have been 2800. Less than 2, so less than 2800. Nearest option you have to select. Less than 2800, nearest option 265. I think that is the nearest option. You please double check the calculation. Here. So the approximate answer will be 2658. I am not using calculator anywhere, but still I can solve it. Okay, so this is smart calculations. Smart calculations will reduce the time in the examination hall. You can quickly answer them Also you can get approximate answers. Okay, look at the options, they're not very close to each other, right? For example, if options are 2658, okay, 2758, 2654, like that, then there is no option, you have to solve it either calculator or leave that question. But here options are having sufficient difference among them, the distance among options is very high, so even approximate calculations can give you the exact answer. Okay, right. Clear? That is question number 47. After 47, next machine's question was 61. Yes, next machine's question 61. Yes, here we have the question. This is a question from transformer subject. Just go through the question. Read the problem. A transformer has a full load copper loss of 400 watt. Then what is the copper loss at half load? Direct question, right? We know copper loss at half load is equal to 0.5 square times of copper loss at full load. Because copper loss is proportional to current or square of the current. Square of the current. When current becomes half, copper loss becomes 0.5 square times. That is indirectly 0.25 into full load copper loss is 400. So is it not 120? Sorry, how much? 100 watt, right? 0.25 into 400, that is 100 watt. So the last option is correct. Simple question. Next, question number 62 is also machine's question only. Read that. A three-phase 400 volt wound rotor induction motor has delta connected stator winding and star connected rotor windings. Stator has 48 turns per phase. Rotor has 24 turns per phase. The standstill voltage across the slip rings is how much? This is an interesting question. Stator is delta connected. Stator is delta connected. Rotor is star connected. Voltage across slip rings. We all know in induction motor, slip rings are connected to rotor, right? To all the three lines, three slip rings will be available. So indirectly they are asking line voltage in the rotor side. To answer that, what is the supply voltage? 400. Correct? What is the turns ratio? Turns are given, right? Stator has 48 turns per phase. Stator 48 turns per phase. Rotor has 24 turns per phase. 24. Is it not 2:1 indirectly? Yes, 2:1. But a turns ratio will always represent the phase voltage ratio only. Okay. Next, primary has a line voltage 400. If line voltage is 400, what is the phase voltage also? 400. If you know primary phase voltage, can you find out a secondary phase voltage? E2. Okay. Yes, I will go to the notes. Yes. E1 is equal to 400 volt per phase. E2 is the question. We know E1 by E2 is equal to turns ratio N1 by N2. E1 was 400, E2 is required. What is the turns ratio we have? Is it not 2:1? Yes, 2:1. 2:1. So I got E2 which is equal to 200 volt per phase. Now, secondary side phase voltage was 200. If secondary side phase voltage is 200, what will be the line voltage? Line voltage, as it is a star connection, can I say line voltage will be root 3 times? So therefore, secondary side line voltage will be E2 line voltage will be a root 3 times of this 200. 1.732 into 200. We know if it is 2 into 200, 400, the answer would be less than 400. Okay, less than 400. So 346. Okay, correct answer, right? So that will be the voltage across the slip rings. But most important thing is this calculation is valid only at the time of starting. This is all valid at the time of starting. If it is under running condition, the voltage would have been S times of this voltage. But nowhere in the question whether a machine is starting or running, nothing was given. Okay, then I'll assume it is starting only because slip information is not there. If it is running condition, at least slip information must be available, right? Slip is 5% or 4%, something like that. But there is no information about slip. Also, starting condition, one of the option matches 346. Therefore, the answer will be 346. Correct? Okay. That is question number 62 from machines. We have 6 more questions. 63. This is also machines question only. The starting torque of a 3-phase induction motor has maximum value. Then what is the rotor power factor? Okay, they said starting torque is maximum. Starting torque is maximum. Can I say starting torque is maximum when SMT is equal to 1? SMT is nothing but the slip at which maximum torque is created. When I say starting torque is maximum, SMT is equal to 1. What is the formula for SMT? R2 by X2 is equal to 1. From this, R2 value and X2 value both are equal. If R2 value and X2 value both are equal, can I say this is a circuit diagram? Remember, this is a circuit diagram at the time of starting. That's why the slip equal to 1. Actually, it is R2 by S. But at the time of starting, slip equal to 1. That's why it is simply R2. But what is R2, X2? Both are equal, right? So here, resistance and reactance both are equal. We know in a series RL circuit, if resistance and reactance both are equal, what will be the power factor? 0.707 lagging, right? Or at least find out power factor angle. How do you find out power factor angle? It is tan inverse imaginary part by real part. As R2 and X2 both are equal, is it not tan inverse 1? That is equal to 45 degrees. Clear? So if it is 45 degrees, then what is the power factor? Cos 45 degrees. 0.707 lag. I think it is correct, right? Tan inverse 1, that is a 45 degrees. A simple rule, right? If resistance and reactance both are equal, the power factor would have been 0.707 lagging. Lagging because it is RL circuit. Okay, so the answer for this question was 0.707. Very simple question. This is the most important data. Starting torque is maximum. That means SMT equal to 1. That means R2 is equal to X2. Clear? So the answer is 0.707 lagging. Clear? Okay. Next we have question 64. This is also from machines only. A 12-pole 3-phase alternator is coupled to an engine running at 500 RPM. The alternator supplies an induction motor which has a rated speed of 1500 RPM. The number of poles of the motor will be how much? See, very simple. An alternator feeding induction motor. We have two machines now. There is an alternator. The output supply of the alternator was given to induction motor. Clear? So as a supply was directly given, can I say alternator frequency is nothing but induction motor frequency now? Coming to alternator, what is the data given? In alternator, we have 12 poles. We have 12 poles and alternator is driven by an engine at 500 RPM. So alternator has 12 poles and driven by 500 RPM. Therefore, what is the frequency generated by alternator? Is it not Pn by 120? So 12 poles, Pn by 120. 12 poles into 500 RPM by 120, is it not 50 Hertz? Yes. If alternator develops 50 Hertz, the same 50 Hertz will be given to induction motor. Therefore, the induction motor frequency is also 50 Hertz. Okay, but what about induction motor data given? Yes. The induction motor has a rated speed of 1500 rpm. Okay, if the rated speed of induction motor is 1500 rpm, then what should be the number of poles? What should be the number of poles? Okay, yes. So coming to induction motor, the speed is 1500 rpm. Let us consider it as ns. So what is the formula for ns? 120 f by p. Okay, actually induction motor will not rotate exactly at ns, very near to ns, so I am assuming. Okay, so 1500 is equal to 120 into frequency. How much is the frequency we got? 50 hertz divided by, I don't know, please don't use this 12 poles here. This 12 poles is synchronous machine poles, but these are induction machine poles. This is induction motor data. Okay, so if you solve it, you'll get 6 poles, correct? Because 2 zeros will cancel, 5 will cancel 3 times here, 4 poles, not 6. The number of poles must be 4. So the induction motor must be designed with 4 poles so that its synchronous speed will be 1500 rpm. Strictly speaking, they should not write rated speed, they should write it as synchronous speed. That is the appropriate word, but nevertheless, poles must be always even number only, it's 4 poles. Okay. Right. Next, we have 3 more questions. Let's solve them. Next, 65 question is also from machines only. The losses in an alternator are more comparable to which machine? Alternator losses are more comparable to which machine? First of all, in each machine we will try to write down what are the losses we have generally. In DC machine we have copper loss, iron loss, and rotational loss will be there because there is a rotating body. In transformer we used to have copper loss plus iron loss only. There are no rotational losses in transformer. Why? Because transformer is a stationary part. Induction machine will also have a copper loss, iron loss, and rotational loss. Induction motor will also have copper loss, iron loss, and rotational loss. What about alternator? Alternator is also a rotating body only. Therefore, it will also have a copper loss, iron loss, and rotational loss. Are you understanding that? Okay, so the only point is transformer will have a very less amount of loss compared to all other machines. Why? Because transformer do not have rotational loss because there are no rotating parts. Transformer will have a copper loss and iron loss only. Our synchronous machine will also have a copper loss and iron loss, but additionally it will have rotational loss. Therefore, the losses in an alternator are more comparable to transformer. It cannot be more compared to DC machine or induction machine because DC machine and induction machine are also having a copper loss, iron loss, and rotational loss. But a transformer has only copper loss and but there is no rotational loss in a transformer. That's why alternator losses are more compared to transformer. Okay. Yes, that is question number 65. Next. Question number 66. This is also from electrical machines only. When alternator operates at a load power factor of unity, what is the effect of armature reaction? We know at unity power factor, the nature of armature reaction is purely cross-magnetizing. Purely cross-magnetizing. It is neither magnetizing nor demagnetizing. It is purely cross-magnetizing. Wholly demagnetizing, wrong. Wholly magnetizing is wrong. Partially demagnetizing is also wrong. Wholly distorted. See, distorted is also known as cross-magnetizing. Anything is same. Okay, so the correct answer is distorted. That is question number 66. Next, question number 67. In a three-phase star-connected generator, if the fundamental and third harmonic RMS voltages in each phase is V1 and V3, then what will be the line voltage? Simple question, guys. This is repeated question in many exams. Machine is star-connected. Okay, the phase winding has fundamental voltage as well as third harmonic voltage. What about line voltage is the question. Yes, line voltage will have only fundamental voltage. Third harmonic voltage does not reflect into line terminals. This is one of the advantage of a star connection. Why alternators are always star connected? There will be two reasons. One is line voltage is higher compared to delta connection. Second thing is third harmonic voltage does not reflect into line terminals when the winding is star connected. So therefore, the correct answer is the line voltage will be root 3 times of V1. Okay, so second option is correct. Third harmonic voltage can be neutralized by connecting the winding into star format. Clear? Yes. The last question we have, question number 69. With this, we completed total 27 questions from electrical machines. See that. A 1500 kVA star connected 6.6 kV salient pole synchronous motor has direct axis reactance and quadrature axis reactance given. Armature resistance is neglected. What maximum load the motor can supply without loss of synchronization if excitation is cut off? They said excitation is cut off. Remember, if the excitation is cut off, as the machine is a salient pole machine. How do I know salient pole machine? Because the XD and XQ calculations are given. If in salient pole machine, power will have two components in it, right? What is the total power? It will be 3 EF into VT by XD into sine delta. This is electromagnetic component. And the next one will be 3 Vt square by 2 into 1 by xq minus 1 by xd into sine 2 delta. This is known as reluctance power. If the excitation is removed, this first component becomes 0 because EF becomes 0. But this reluctance power will be available. Then the machine is known as reluctance generator. Am I correct or not? So therefore, when excitation is removed, the power will be 3 Vt square by 2 into 1 by xq minus 1 by xd into sine 2 delta. But in the question they are asking what maximum supply we can give. What is the maximum load we can deliver? Can I say maximum power can be generated when delta is equal to 45 degrees? If delta is equal to 45 degrees, then only this sine 2 delta component will be maximum, that is equal to 1. So therefore, the maximum power that we can deliver is 3 Vt square by 2 into 1 by xq minus 1 by xd. This is the maximum power. Okay, in this Vt is already given in the problem. What is Vt? 6.6 kV. Remember, this is line voltage. So therefore, phase voltage will be 6.6 by root 3 kV. XD was given, XQ was given, 23.2, 14.5. So therefore, I'll go to the next page. P max is equal to, I will rewrite the formula, 3 Vt square by 2 into 1 by xq minus 1 by xd. Why I am multiplying with 3? To get 3 phase power. So it is 3 by 2 into, what is Vt square? 6.6 by root 3 kV. kV means 10 power 3 whole square into 1 by, what is xq? xq was 14.5, xd was 23.2. It is 14.5 minus 23.2. Okay, so you may be wonder, sir, how do I solve it without calculator? You can solve it, approximately solve it, nearest answer you can select, right? So can I say root whole square is there, don't forget. Can I say root 3 square means 3 will cancel? Then it will become 1 by 2 into 6.6 square into 10 power 6 into, can I treat 1 by 14.5 is approximately 1 by 15. This is approximately 1 by 25. Right, just approximations. Then it will be 1 by 2 into, what is 6.6 square? 6 square is 36, 7 square is 49, maybe around between the two, right? 6 square 36, 7 square 49. Now 6.6 square means in between the two. Maybe 40, 42, something like that, approximately. Okay. Uh, it will be 25 minus 15 by 15 into 25. Correct? Okay, 25 minus 15, that will be 10, correct? That 10, I will go to the next page. I am not leaving it. As it is difficult, I don't leave it. I am trying to solve without calculator. Okay. So 1 by 2 into 40. Is it not 1 by 2 into 40 becomes 20? So it will become 20 into 10 power 6 into what is remaining? 10 by 15 into 25. So that I'll get approximate value, right? So 20 into 10, is it not 200 into 10 power 6 by 15 into 25? I think 5 will cancel here now. 5 will cancel 40 times here and 5 times here. Again 5 will cancel 8 times there. It is 8 into 10 power 6 by 15. It will be 8000 by 15 kilowatt. 8000 by 15 kilowatt. 8000 by 10, 800 kilowatt. 8 by 15 means maybe around 500, something like that. So what is the nearest answer? 563, I think. Just let me check that. Okay. I'm getting 8000 by 15. 8000 by 15. Again 5 will cancel there. 3 times in the 400 by 3. Right? Around 533 something I will get. Are you understanding that? Again 5 will cancel here, guys. Right, worry. 3 times 400 times not 400, I think I made a mistake. 5 will cancel 1 time 30, 1600. 1600 by 3, more than 500. More than 500 kilowatt. 563 is the nearest answer. If you do everything exactly, you'll get 563. Guys, please understand how to use smart calculation. First of all, the total power in salient pole machine will have 2 components in it: electromagnetic power component, reluctance power component. But when excitation is removed, electromagnetic power component becomes 0, only reluctance power will be available. But the question is, what is the maximum power we can deliver? Can I say maximum power is possible when sine 2 delta is equal to 1, that is delta equal to 45 degrees. Then the remaining power is known as maximum power. And Vt is already 6.6 kV, that is a line voltage. I just substituted the phase voltage. I took approximations to get the exact answer, nearest answer. I know most of the students will leave this problem because 14.5, 23.5, they are, calculations which is difficult, but actually you can solve it within 1 minute. It is not so difficult. All right. So that's it, guys. Total 27 questions we solved from electrical machines subject. Okay. So this shows how important core subjects are when it comes to PSU exams and state services exams, ISRO exam, BARC exam, something like that. But in gate level exams, you'll get less weightage. Machines overall, you'll get 11 to 12 marks only. You don't get more than 20, something like that. Because gate means a lot of other subjects will be there. Signals will be there. EMF will be there. Analog circuits will be there. Digital will be there. Every subject should get some questions. So you'll get little less weightage. 10 to 11 marks you can get from electrical machines. But these kind of exams, core subjects will play a major role. Okay. So with this, I am concluding this lecture. Thank you very much.